computer.
Yes.
Electronic.
Yes, we're trying to avoid the first of everything. Everything's the first if you qualify. And this is going to be quicker, but 20 minutes to do in 1 minute. The Harwell Deckatron machine. Let me whiz forward. That's the machine we're going to talk about. This is one of the iconic photographs of the machine in use. I'll come back to that photograph shortly. I'm going to talk about the history of the machine, and then we'll look at the restoration and the operation of the machine when we're next to it. Frankly, I ended up more interested in this part. So why was the machine built in the first place? What was the requirement? Bit of its history, anything to do with atomic energy, nuclear power, fission was European discoveries. And bulk of those scientists who were involved were shipped off to the Manhattan Project to build the weapon. There was an agreement, though, that that information would be shared with the UK afterwards. However, by the time Truman in the States was president and after he's our Prime Minister, that agreement had been lost by the Americans. The Americans actually then enacted something called the McMahon Act, which actually stopped any sharing of information at all. So the UK is completely shut off. They provided all the information, the scientists over to the Manhattan Project, and then are shut off. The decision was made by Bevan, who had a really rough meeting with the Americans, that we had to have this bloody thing here, and we had to have this thing here, and it has to have a bloody Union Jack flying on top of it. That was the decision that was taken to actually build, or to start the UK's nuclear weapons programme. There was a formal decision in '47, but it wasn't actually ever mentioned for about a year later. So, we needed to build an atomic energy research establishment to actually sort of generate start that research again in the UK. And RAF Harwell, which was RAF base in 1935, just south of Oxford, was chosen. In charge at the start was Sir John Cockcroft, or John Cockcroft at the time. He wanted the research establishment over near Cambridge. He was a Cambridge man. The RAF wouldn't give up any of the airfields that side of the country, so he was presented with Harwell. Lots of stories very quickly. It was Mark I in terms of these new airfields. You know what Mark I's like. The runway was actually over a hill, so you couldn't see the end of the runway when you were taking it off. But that's okay, because if you take it off, that's fine. However, if you had a problem, the ammunition dump was at the end of the runway. So if you weren't taking off, there was a sort of pretty sharp turn into the grass at the end of the runway to avoid it. But anyhow, it was successful. Very frosty reception from the people at RAF Harwell. John Cockcroft was given the keys and told to have a look round. The abiding memory of everybody at Harwell at the time was the mud. This is the sort of the ridgeway, it's sort of chalk, fairly up underneath the topsoil, the mud, the work and so on. The most obvious site, the first thing that was built at Harwell is that chimney, just to vent hot air. All the fundamental research, a lot of the fundamental research of nuclear fission had been done in the UK and in Germany before the war. That was almost scrapped by the Americans, really. The sole job was to produce the weapon, to produce plutonium, to produce the weapon. So huge amounts were just not understood. Nobody understood actually what sort of fission fragments actually were when atoms under fusion, and how to build reactors. Now that reactor, it's called GLEEP, the Graphite Low Energy Experimental Reactor, was built at Harwell. It's the first thing they actually built. It first went critical in '47. It was a tiny reactor. It's a big box, but the reactor's actually quite small. It's only 3 kilowatts, which is a sort of 3 kilowatt. But it was the most stable reactor that has actually ever been built. So neutron flux out of it was absolutely constant, and it was used for actually all of the calibration of test equipment until the 1990s. It should have been kept as listed and kept, but it wasn't. It was destroyed, which is a real shame. But it was the start of understanding how to decommission power stations, and GLEEP was the first one they used. It's desperately slow. As I said, none of the a lot of the research had stopped. So there were fundamental things about half-lives of fission products, half-lives and the chemistry, for instance, behind plutonium, as well as the nuclear side. There's the whole metallurgy chemistry side. The only tools that were available to them were the odd mechanical calculator, very few electromechanical calculators, and the biggest source of information were tables, printed tables, a lot of which had come from generated as part of the WPA program in the States. But these tables, they're that big, bound books, very valuable, and not available for everybody at Harwell, a limited supply. Also, Harwell at the time was employing vast numbers of maths graduates straight out of university, with a bright, shiny new world of atomic power. Unfortunately, the bulk of them were sat in a huge lab with a mechanical calculator, grinding through problems for weeks on end. I mean, desperately sort of boring work. And a chance encounter between John Tate of the theoretical physics group, literally over the garden fence with his neighbour, a chap called Edward Bennett in the electronics group, saying, couldn't we do something to automate these calculations? I didn't mention the time, this is 49 when this is happening, so limited opportunities to do this. However, EDSAC was running at the moment, and our three design engineers, Ted Cook-Yarborough, Gunny Thomas and Dick Barnes, would travel over to Cambridge to actually look at EDSAC. They put together a case using the technology that they knew at Harwell and presented the case to head of Harwell, John Cockcroft, and the head of theoretical physics, Klaus Fuchs. The story is that it was very different. Normally you'd go to do a presentation on this sort of thing, different labs and different teams, and it would be a big knockabout session, lots of discussions about would it work and the expense and the commitment to it. This was a very subdued meeting, and after about 45 minutes, John Cockcroft said, "Do you think you can do it?" I replied, "Yes." He said, "Well, go away and do it." So there was a bit slightly odd but left. It was only discovered that morning, Sir John Cockcroft had only been told that Klaus Fuchs was actually admitted for spying for the Russians. So it was obviously a difficult time. Fuchs, I must say, the slide, Fuchs is quite a hero. All of that knowledge that was built up in the Manhattan Project was not shared with the UK, as I mentioned. Klaus Fuchs kept very, very detailed notes, possibly to share with his Russian counterparts, but those notes were actually valuable to actually restart research in the UK. They started building the machine in 1950. You'll see the machine is very, very well engineered. These guys knew how to design something that would work from the start, and very high quality engineering. You'll see that for the moment. It's completed in 51. It was completely designed before production started. Production was shipped out to the companies working around Harwell and was commissioned very quickly. Control orders, it's a pretty standard machine in terms of order code for that period. We can test for store, we can do conditional jumps, unconditional jumps. Tape readers, I'll look at that in a moment. We can search for we can switch control to different tape readers, and we can transfer control to tape readers. We can print the accumulator, we can stop. Hardware multiply and divide, as well as addition and subtraction. Typically, a program for a machine would look like this. The machine can operate in two ways. It can either operate from paper tape, and in which case you could describe it as a sequence control calculator, or we can transfer the code actually into the Deckatron stores, which you'll see later on, and run code from stores. So it's quite capable of operating as a stored program machine. So typically on a job like this, you'd have 3 tape readers. The first one would act as the bootstrap, clear the stores, get things set up. That would then transfer control. Oh, it's reading actually constants from another tape reader. But it has a subroutine. And literally on the subroutine, it would call the subroutine on another tape reader, and then transfer control back, turn from subroutine typically. However, and this is what makes it fantastic used in education, that's a tiny subroutine. It's literally a paper tape glued end to end, and that would be called, run the actual routine, and then transfer back to the controlling program. More often than not, subroutines they would have two, almost like dustbins either side because of the length of the things. These are also mechanical tape readers. So after a while, they will actually punch their way through the tape. But particular routines and library routines, they punch onto Mylar. Ted Cook-Yarborough published the operating experience. This is a desperately slow machine. Multiplication can take, give correction, but the best part of 10 seconds. So, but it was incredibly reliable. More often than not, it was left over Christmas, New Year, over weekends, printing out these tables. There is this discussion about, I think it might have been Maurice Gould who said, well, okay, EDSAC might only run for 20 minutes before it fails, but it can do about a fortnight's work that the Harwell machine had done in the meantime. But pretty good. The 5 weeks damage is because the head of the group, Ted Cook-Yarborough, on his own one evening, was climbing on a step ladder behind the machine to take a store off, and then fell and knocked the whole lot over. The general reaction from the team was that thank God it wasn't one of them, and it was the head. The machines had a charmed life, like 4 minutes. The machines had a charmed life. It was replaced fairly quickly in '57. Harwell had built their Cadet, their first transistorized machine. They were buying machines off the shelf, and they had access to faster machines out at Aldermaston. But there was a design not to actually scrap the machine. So the machine was actually put up as a competition for colleges, universities to make a bid for this particular machine. 30 submissions, shortlist of 9. More often than not, the 9 turned up with the local mayor in chains and everything. But it was won by the Wolverhampton Staffordshire College of Technology. They were, now this is important. The chap in charge at Wolverhampton was very PR conscious. So every opportunity, he would have something in the papers, pictures and so on, and that's incredibly valuable for us. The information prior to that date is a lot more sketchy. I don't think they knew what they'd won. They suggested, for instance, it could work out wage calculations more quickly than human beings. That's a tad optimistic. I really don't think they knew what they'd done. However, they used the machine to start the first undergraduate computing course in the UK. Oh, right, slides agree with me, in '65. Lots and lots of press coverage in the local paper, Birmingham papers. They renamed it the Witch. The Wolverhampton Instrument for Teaching Computing from Harwell. So I tend to call it the Harwell machine, people call it the Deckatron machine, or people call it Witch. They were very proud of it. Back to this iconic picture. This is a time, chap on the left is a chap called Peter Burden. We'll come on to Peter in a moment. He was waiting to go up to Cambridge to read maths. He just finished his A-levels at local comprehensive school. At the comprehensive school, local grammar school, and had seen the machine on visits to the college. They were approached by Chubb, the people that make mortise locks, who are local to Wolverhampton. There are certain problems in the designs of locks that you need certain combinations so they're less brittle, and the Harwell machine was used to work out the patterns. So their application, they did actually fulfill that idea of actually supporting local industry. Peter Borden we'll come on to. He was a student at that point. This was May. He was about to go off to Cambridge in September. By '73, Wolverhampton had bought themselves an ICL 1900 and an IBM, something or other. And again, absolutely nobody wanted to actually destroy this machine. So it was transferred to Birmingham Science Museum. again, this is an example of what, which computer earns part retirement. And apparently, then the IBM played a tune and the ICL produced artwork. But it was listed by Wolverhampton as the world's most durable computer in the Guinness Book of Records at 73. It went on display at Birmingham Science Museum. Now, I'm sort of the geeky sort of person that actually spent every weekend at Birmingham Science Museum. My mother reckons that's me, but I don't think it is. But it's probably about right. It was on display. It was never actually working. There was an idea, and there's some odd letters in the archive about Birmingham trying to get it to work, but they really weren't committed to it. And it went back into storage in a pretty sort of grotty storage centre in the centre of Birmingham. Now, this picture is zoomed in from a set of pictures that Chris Burton made when Chris was visiting the museum store to look at the Heck computer. Now, I was looking at these pictures many years later and zoomed in and saw that control panel. I thought, oh, I actually recognise that. I know what that is. So we arranged to go back to Birmingham Museum's Collection Centre, and everything's piled in together, really. Right at the back, I'll point to that one, over the top there, you can just see part of the witch. So we have to move all of this. This is an Orion machine, there's a Bryant disk drive behind it. All of that got taken out, and then we found bits of the machine just lying on the floor, cables cut, things broken and so on. Lots of the other bits of the machine, several visits actually to try and rescue everything, but we were fairly well encouraged. The decision about whether to actually restoration of this machine was possible. So certain questions, similar questions have been asked before already. Have we found all, or at least sufficient hardware? We didn't imagine we'd find all the hardware, but we thought we might find sufficient. Do we have any access to manuals and diagrams? We didn't at that stage. Are the original designers available to help? Can we contact them? Do we have everything we need? Important things about restoring the machine: people, skills, time, the finance, and the space. And if we restore the machine, what we're actually going to do with it, should we attempt the project. Luckily, as we were searching through top to bottom to this museum store, we found this pallet, and it contains spares. And we thought, these are spare valves, there are spare paper tapes. It's difficult to see on this, but this is about 18 inches deep. Right at the bottom of this is a huge bound book on the theory of operation of the Harwell machine, which has all the circuit diagrams, prose descriptions of how the machine works. And I thought, oh, well, it's a gift now then, isn't it? Slightly oddly, it also it obviously dates back to Harwell days, because in one corner there was a little box surrounded by lead bricks. So it was very tentatively took the lead bricks apart with one of the two easels, opened the box, there was nothing in it. Very carefully get the lead bricks, and it was a surprise from Harwell. We also, because of the BCS, managed to actually get in touch with the designers. It's my colleague Tony Fraser, the laptop, Dick Barnes behind him, and Ted Cook-Yarborough. This is at Ted's house in Abingdon. Dick had also kept a record of all these sort of press cuttings as well. So part of the picture on the left there is me comparing notes and what we've researched so far. They were both thrilled, absolutely thrilled about this. This was going to be restored. They were very, very helpful. Came to the museum several times. Oh, God, it's 20 past. We put together a proposal for the CCS, which was accepted. We put together a proposal for the Birmingham Museum's Collection Centre, which went in May, and in July they agreed. And eventually we transferred the machine back to TNOOC in 2009. Skipping on, because we'll talk about the machine later, we had a reboot day, which was Ted Cook-Yarborough on the right, Dick Barnes, me in the middle, one of the mathematicians from Harwell, and that's Bart Fossey. And remember the 18-year-old Peter Burden on that picture? That's Peter Burden on the left. Peter Burden went to Cambridge, did his degree, went into teaching, and eventually got a job back at Wolverhampton College of Technology using the machine. Fantastic day. I'll talk about the race this afternoon. and then the machine today, which we'll go and see later. Right. Oh, that was a very nice, but
That's great. I think we should restart at 2 o'clock.
I think so, yeah.